Okay, I guess we better get rolling here. See if anybody else shows up along the way. Let's see where to start. Welcome. Welcome back. Let's take a look at the syllabus. Just there are some changes that I want to point out. Most of it will look familiar. Let's see, there it is. We'll share. Okay. Let's position some things here out of my way. All right. So you all know where to find me. That's what the blue box is all about. Office hours and the meeting ID is the same as it was last semester. Everything's going to be online. I mean, even the lab. And while I'm here, while I've got that stream of consciousness, what I want to do is all the labs are web-based, but I do want to meet right after we finish here at I guess that'll be 1 o'clock. No, 12. 9 to 12, and then 12 to 1. If you can make it, it's voluntary. So I want to have a Zoom meeting at 12 o'clock to talk about the lab. And after that, I'll do like I did last semester, and those meeting times will still be voluntary, but you don't have to show up unless you're having a problem. And actually, you don't have to show up at all if you've got other obligations, because I'll be recording everything. You may notice a longer delay in posting of the recordings. For some reason, it's taking me longer to process the videos. Not that they're available any later, it's that my approach to processing them before I make them available on Blackboard is taking more time. Okay, so let's see. I assume everybody's got Cengage Unlimited from last semester, so that shouldn't be an issue. Hard copy's the same. Calculator's the same. Requirements for the course, you're going to need, of course, a PC, a laptop, or tablet. Yeah.
Oh, Dr. Bly, sorry, I didn't mean to interrupt you. I could get into my homework, but I couldn't get into my book for some reason from last semester.
Oh.
Should I contact them?
Yeah. Do you still have Dee's contact information?
Maybe. I'll have to look.
Okay.
I think I had it written down from like the beginning of the semester in one of my notebooks. I'll look through it.
If you've contacted her before, then you should have an email in there with it.
Oh, yeah, that is right. Yeah, I should be able to do that. Never mind. Yeah.
That's the way I do it. I just go back and look at
yeah.
Search for an old email.
Yeah, but I had it written down too. But okay, thank you.
Yeah, and I've run into some problems with Cengage this year. Actually, more of the problems have been with the bookstore. And
doesn't surprise me.
Yeah. So the outcomes and the contents that of course they have changed because we're in a new course. But all the exams are going to be Blackboard native exams. I think the last time, the first semester, I was using the PDF files that you would complete and then upload those. But now I've got, at least for this course, I've got all the exams in Blackboard. So they're native Blackboard exams, but they have to be proctored. So I have Respondus Monitor Lockdown Browser is monitoring them. If you've never used that, I've got an appendix that explains in nauseating detail how to set up Respondus monitor and how to take the test that way. Plus, when we get into Blackboard, I'll show you there's a practice test that helps you weed out problems with your technology before you actually have to take an exam. So I'll point that out when we get to it. Let's see. Homework's is the same steps that you need. There won't be a final exam. I couldn't fit it in. There's just not enough time. So chapter 18 on electrochemistry is your last test, and it'll be in the final exam week. Okay, similar things here with how your grade is determined. Chapter exams are worth 70%, homework's worth 20%. You get credit for attending, so I have to know you're here. That's why I want to see your picture at least at the beginning, and then if you have to drop out, that's okay. You have to drop out your picture. I don't want you to leave the building. And there's a syllabus test. So I don't remember if I had one last semester, but it's worth 1%, and it's a fairly easy 1%. Okay. As always, check your email every day, and that's the school email, because there may be vital information that shows up in the emails. Okay, so if you find yourself somewhere that you can't go into Blackboard and the course and click on Zoom and just click on the meeting, then this is the information that you would use. Say you're out somewhere unexpectedly, you want to connect with a meeting, use your cell phone, then you would need your Zoom client loaded on your phone. There's in one of the appendices, it gives you the link for the Zoom client if you don't already have that. And then it'll ask you for an ID code, and this is the ID code for the course this semester. Plus, I've added a passcode, which is like a password. And that's just standard across the college now, because several of our meetings have been bombed, and it's not a pleasant experience. So now we have passcodes. So you need both of these numbers to get in if you're not coming in through Blackboard. Okay, so the schedule is similar in appearance to last semester. Here's your syllabus test that's worth 1%. You know, it's due by, I guess that's next Monday. And all the exams and homework due dates are in yellow. Let's see, there's some other useful information here. Spring break is this time, and that's when your mid-semester grades are due. So you know anything above that goes into your average. And then this is when final grades are due. These are the topics we're going to be covering. So today I've got to get through class business, plus I've got to cover chapter 10. And I'm a creature of habit. So if the class time runs out and I haven't finished the lecture, I'm just going to keep talking and recording. So if you have other obligations, you've got to leave, then go ahead. You can come back and watch the video as soon as it's posted. Okay, let's see. That's standard stuff. That never changes. Makeup testing is kind of a moot point for online. You take the test. Oh, you take the test when you want to. And when it says exams on these days, that's just a last day. Beyond that, you incur penalties, but you can take it before then if you want. It'll be available. Let's see. I've got it set up, and I'll show you in Blackboard. I've got it set up so that you have to take the exams in sequence. You can't skip one. Like something gets in the way, you run down the line, and now you're at exam 3, but you still haven't taken exam 1 or 2 yet. Believe it or not, some students do that. And they go back and try to take exam 1 and 2. Well, I've got it set up now so that you can't take them that way. You have to take them in sequence. You got to finish exam 1 before exam 2 will open up, and on down the line. So that begs the question, what happens to exam 1? There's no exam before that. The syllabus test. You take the syllabus test, then exam 1 is available. Okay, so back down to where I was located before. Exam etiquette, of course, you're going to be recorded by Respondus monitor. So you need to sit up in a upright position. Don't recline on your bed. Wear street clothes. Don't have light background. Have light on your face so the system can recognize your face. Otherwise, it'll flag you as missing from the scene. And I'll have to go look at it and say, okay, that's all right. He just didn't follow instructions. Let's see. This is how you connect with my office hours. If you're not coming in, well, this is the only way, actually. I don't have a Blackboard link for my office hours, so you have to open the Zoom client, put in this ID, and connect. Now, with one caveat, it's going to be probably another week before I finish producing all the videos for the labs. So during Tuesday and Thursday office hours, I'm not going to be there. I'm going to be on the Beaver campus producing the lab videos. But after that, things should settle down and I'll be available. Here's the, let's see. Yeah, this is your link for the Zoom client, right? So just go there on your tablet or your PC or your laptop, you go there. If you need to put it on your phone, I think you go to the App Store, whatever, if you have an iPhone or an Android, go to the App Store and just search for Zoom client and load it on your cell phone in case you need it. This is all standard stuff. And here are the appendices. Okay, the first appendix has to do with setting up your Cengage Unlimited homework. So you've probably all got that, your old hats at that one. I don't know why I put this one here. I don't think. No. All of your homework is, no, this is true. This is true. End of chapter problems. So for this class, those are the only ones that are graded. Anything else you see in OWL should be marked ungraded. And the only one that's graded is end of chapter problems. The ungraded ones are there just for practice or information if you need to find it. Find extra stuff or work extra problems, that's where they'll be. I don't know why I kept this one in here, because that's a mastery screen. You won't need that at all. Okay, Appendix 2. This is attending class using Zoom. So this is the non-Blackboard connection. This is the Blackboard connection. So that's some more detail. 3 is, you probably already know about this one too. Setting up your side-by-side screens so you can see the shared screen on half and me and my whiteboard on the other half. And that's the format that I'll be producing the video. So when I splice them together, I put the shared screen on half and I put me on the other half so I'm big enough that you can see what I'm doing on the whiteboard. But those are the steps for doing that. And the last one is how you set up Respondus Monitor Lockdown Browser. You can't use a Chromebook or a smartphone with Respondus. So you've got to have a PC, a laptop, or an iPad, or a tablet. You can use a tablet with that. Let's see. This is an instructional video. Okay, if you don't already have Respondus Lockdown on your computer, you have to go to this website, this link. This special ID is only valid for New River. If you don't load it from this site, then it won't work for you in Blackboard. It knows, because we have to pay for the service. So they make everybody load a different version. So you've got to load it from here. And then there are details here depending on what kind of computer you have. This is for iPads. Everything below this if you have an iPad. There's some instructions on technologies, different type of technologies. You may have to enable your webcam if it's not built in. If you have a laptop, then of course it's automatic. But if you have an external webcam, like I do on this computer, hopefully Respondus will recognize it. But if it doesn't, then these are steps for enabling it. And at the beginning of every exam and your practice test, there's going to be a security check. And so it knows you are who you say you are, and then it takes a snapshot of your face, and that's what it uses for comparison with you during the exam. So if somebody else slips in, they don't fit the profile that you established at the beginning. And that's what the practice test is for, to give you experience doing that. All the tests are going to ask for a password. Right? I've tried without passwords in the past, and it just creates problems. So the system apparently is expecting a password, even though it says it's optional. It expects a password. So the passwords I always give are the CRN for the course. So this is CHEM102, course reference number 22915. That changes every semester, so I have to change that every semester too. But it'll ask you, and that's the number you put in. Some notes on protocol, and that's it for the syllabus. Any questions? Hold on a second. I need to take this call. Hello. Yes, ma'am. Yes, we'll be there. Will do. Bye. Doctor's office. Sorry. Okay. Any questions before we move to Blackboard and show you some of the changes that have occurred between Chem 101 and 102? Okay, I'll stop the share here. And good, we're still recording. And then I'll share Blackboard. If I can remember where I put it. I think it's here. Yeah, this is it. So everybody recognizes that. It's where you connected, I'm assuming. So I'm gonna close that. So we're gonna go into Blackboard. And of course, this is the instructor's page. So you see a lot of garbage here that you're not gonna see when you call yours up. And I think I'll go into student mode until I get to a point where I have to do instructor mode. Okay, so this is what it's going to look like for you. All right, start here. Same, I put the connector for your email so you can contact anybody in the class. There's your Zoom connector. Okay, syllabus and my schedule there just as usual. No changes there. I've duplicated the schedule here so you don't have to pull out your syllabus to find it. If you don't have a PDF reader, this is where you get a free version. This is the Acrobat version. This is a third-party version that works pretty well, Foxbit. You probably already know that when you install these things, these free things, they're going to try to slip some ghost software in on you. Let's see. I'm checking. I think I lost somebody. Yeah, I lost Justice. No, there's Justice. 1, 2, 3, 4, 5. Ah, okay. Sheets, Simmons. Oh. I'm missing Cody and, yeah, I'm missing Cody and Sue Young. Okay. All right, so let's back up. We'll use our breadcrumbs and go backwards. All right. So I've made a discovery about this free Microsoft Office 365. It's definitely free, but you get what you pay for. And a lot of the functionality for the programs in Office 365 loaded from here have been removed. I found that out the hard way with Microsoft Excel in my CHEM101 class. It wouldn't do the statistical analysis that I wanted for my class to have in there in that first lab exercise. So it's okay. I mean, it's a bare bones Microsoft Office, but if you can afford it, I would suggest finding somebody with student or instructor pricing and buy a full version. I don't care too much for Office 365. That's why I still have an older version. But if you get the full version, then you'll have full functionality. These you've seen before, having to do with OWL. Go here to set up your homework if you're not already, if you haven't already done that. This is, let me see. Okay, these are some more videos. You probably already looked at them, but I'll just point them out. How do you complete an assignment? Chem Doodle, if you have to do any chemistry drawing to answer a question, then you need to know how to do that because the system is really finicky. And it's got to be just so, or it says it's the wrong answer. Now, if it does that, and you still think you've got a right answer, then when you're in your homework, I think you can send me an email from inside OWL. And what it will do is when it contacts me, it'll tell me which problem it is and which chapter it is and take me to that spot in OWL so I can see exactly what happened. Okay, enough said about that. I think this may connect you with the ebook. I haven't checked it recently, but I believe you have to be registered in OWL perhaps before you can connect that way. Here's your homework. And I've set up connections so you can go straight to each chapter. Right? And they're all end of chapter, I believe. Yep. Let's see. Here's the lectures and reviews. So for the first exam, in fact, I probably ought to put exam 1, exam 2 in here like that. But in order, that's exam 1, exam 2, exam 3, exam 4. And we're going to have chapter 10 and 11 in exam 1. And inside there, I've got separate folders for each chapter. And these are, let's see, May, that was 2020. I need to mark this one as previous semester. I do that so that you won't waste your time looking at videos that are ancient, but you can go back and check them if you want. So I'll change that and mark it previous semester, and then the next video you see should be a current date, like today's date. And then of course, this is standard stuff, PowerPoints, 3 flavors, reviews. I left the reviews in there. The reason being that the Blackboard exams are basically extracted from existing hard copy exams. I found that to be the quickest way to get that into Blackboard. So if you study these like you did for Chem 101, it will prepare you for the Blackboard exam. The problem with the Blackboard exams is there's no place in there to actually show your work. So I typically don't ask for that. I know it's a failing of the system, because sometimes it's good to know that you can work the problems. I'm just hoping that you are mature enough to actually work the problems and not just memorize answers.
Will there be a time limit on the test, Dr. Bly?
Yeah, I set time limits, but they don't automatically submit when the time's up. I know that's an option, but I don't do that. You can go past the time limit, and you won't be penalized for it.
Okay.
What it does, though, is if you finish before the time limit, Blackboard grades the exam and puts the score in the grade book, so that you and I both can see it. If you go past the time limit and submit, then it just puts a little placeholder icon in your grade book until I have a chance to look at it. And what I usually do is just go in and see, okay, they finished, it just took them more than 2 hours, say. And then I accept the grade, and then it pops up.
Okay.
So there might be a little delay if you go past the time is all.
Okay.
Okay. There's an extra video on closest packing model. That may be the same one that's in the PowerPoint. I'm not sure yet. And then chapter 11, this is the same stuff. Same format, arrangement. Okay. So let's go back, and each chapter is set up that way. Notice there were no exams in those folders. I pulled the exams out into a separate folder because they're all Blackboard exams. And I put those over here. Now, when you open up the exam, first of all, this is a video on how to install Respondus Monitor Lockdown Browser. You can either do that or just go to the syllabus and follow the instructions, whichever, suits your synapses. Notice that in the exams, the only one that's available in student mode now is the practice test. So the others won't be open up until you do them in sequence. So that means there should be a syllabus test around here somewhere. Let me see where it is. Practice, here it is, syllabus test. Okay.
For up to $10,000. So if you are
So you have to finish the syllabus test, and then the first exam will open up. The practice exam, it wouldn't make any sense to restrict that one. You do that one whenever you want, just to make sure that your technology is working, and you can take it several times if you want. It may give you a grade because there's only one question in there, and it's a question that can have different answers. So you just just put in whatever answer suits you and ignore the grade. The grade doesn't matter. Okay, so you got to do this syllabus test. And this can be taken without lockdown browser, the syllabus test. So you can do that one first if you want. And then you can mess with the installation of Respondus and lockdown and go to the practice test. Okay, these are a bunch of supplemental documents, and they won't all be useful at this time. You've already seen this one, know these symbols in 101, so you've got all the symbols memorized. It's just there if you need it. Review of nomenclature rules, right? You've already had that. Stoichiometry, aqueous solubility, naming doc. These are all things that you've seen in first semester, right? So they're just there if you feel like you need to review and you don't have to go dig through your records to find old stuff. Of course, it's all in the textbook too. Man, it's not as well written in the textbook as you get it from me, of course. Self-help is there. These are end of chapter problem solutions. I mean, if you really want to go in and work end of chapter problems, a lot of them you'll see similar format to the end of chapter problems in the OWL homework, because that's where they get them. They go in there and extract those things and build their homework set from the textbook. Okay, any questions so far? Let me drop out of student preview, and then I can show you what the exams look like once they open up for you.
Will we have extra credit this semester too, or?
Within the exams, possibly, yeah. I don't have any separate extra credit projects like I did last semester.
Okay.
Okay, so this is what it looks like for the instructor. And I want to go down to exams because that's where you didn't see anything before. So there are all your exams, and they'll pop up one at a time as you complete each one. And notice this little thing in here, adaptive release. Adaptive release is what allows me to restrict access to keep them in sequence. Okay, and notice that one's grayed out. The final exam's grayed out because there's no time for it. And I'm sure you're all heartbroken about that. Okay, I don't see anything else except you may recognize all these grayed out exams. That was the format for Chem 101, and it used to be for 102, but I found myself with a little extra time the last time I taught this course, and I was able to convert things into Blackboard testing. And I'd like to do that for 101. I just don't have time to do it right now. It's a very time-consuming process. Okay, any questions on this before we get into the chapter 10? Let me, while you're thinking, I'm going to check my list again to see if, let's see, 8, 1, 2, 3, 4, 5, 6. Yep, everybody's accounted for. All right. So I'm going to, what am I going to do? I'll stick that over here on the side. And we'll stop this share. And we'll share PowerPoint slides. And actually, we're doing pretty good. That gives me an hour and a half. And hopefully, I don't know, sometimes I feel like I'm a gas. You know, I expand to fill the space I'm in. So if I've got an hour and a half, I'll probably expand to take up the whole. Finishing early is not customary with me, but it does happen occasionally. Okay, so let's share the PowerPoint slides. Where are they? Show all windows. Okay, here we go. Let's make a slideshow out of this. Oh, try it again. There we go. So if I don't hear any screaming and crying from the other side, I'll assume you can see this. Chapter 10, Liquids and Solids. Okay, we're picking up from our discussion from, I think, chapters 8 and 9 last semester, which had to do with bonding. And in particular, bonding within molecules, the intramolecular bonding. Okay, and the bonding that holds molecules together. Remember, basically what we're talking about with molecules is covalent bonding. Because ionic bonding, while a valid discussion, involves ions that attract one another, but they don't really behave as single units like molecules do. In other words, how do we know that? Well, you can put an ionic solid that is soluble in water, put it in water, and before too long, it's just ripped apart. If that were a molecular compound like table sugar, it would dissolve, but the sugar molecules would still be intact in the solution. So the bonds that hold molecules together, covalent bonds, are much stronger than any of the other types of bonds, including ionic bonds. So now we want to look at the intermolecular bonding. That is, how do molecules interact? Remember, the kinetic molecular theory assumes that molecules are just billiard balls. I mean, when they approach each other, they just bounce off, no interaction whatsoever. Okay, that's good for a theory, but in reality, molecules do interact. And that's a whole spectrum of interactions. And those forces that are exchanged between molecules are much weaker than the bonds that hold molecules together. If that were not the case, then molecules would just fly apart. They couldn't hold themselves together under the influence of these intermolecular forces. So we're talking about much weaker forces. And now we'll invoke the dipole-dipole forces. In other words, a molecule is not necessarily, it can be, but it's not necessarily possessing of equal distribution of electron density throughout the molecule. Very often, particularly if the parts of the molecule are of different electronegativities, then you will get an uneven distribution of electron density toward the more electronegative side. You can talk about that in terms of the bonds and of the whole molecule. Remember, how do you tell whether a molecule is polar or not? You need to have polar bonds, and you need to have the right geometry. I hope you remember some of that. Okay, so molecules that have uneven distribution of electron density, like that. So this big bulb up here is more electrons and less electrons, fewer electrons down here. Let's say, just for argument's sake, that this molecule only has 2 atoms in it. So you have an atom here and an atom here, right? And they're bound together. So this side would be the more positive side because the electron density is shifted to the other side. Okay, so if this is a pure substance where you only have that molecule, then all the other molecules are going to be similar to it. And if we encounter another one, they interact. They attract one another. that's a dipole-dipole interaction. Okay, so the forces involved are dipole. Dipole-dipole. I know it doesn't say on this slide, but you can also have dipole ion interactions. Right, say if now you have a solution of ions like that, then you can get interactions there between the negative and the positive. Now these are not complete charges, right? That's why I use that little delta. They're partial charge. But that's what happens when you put table salt in water. You get a dipole ion interaction. Now, the spectrum of forces, the strength of forces for dipoles runs a broad spectrum. And the strongest of those bondings are given a special name called hydrogen bonding. And of course, hydrogen bonding requires that part of that mix must have hydrogen involved. Water is a perfect example where you have oxygen bound to hydrogen, and oxygen's more electronegative than hydrogen, right? Because it's far to the right, right? Lower left to upper right, increased electronegativity. Then you get a dipole like that and a dipole like this with the bond, and consequently vector summation of those dipoles gives you an overall dipole for the molecule toward the oxygen. So any other molecule that arrives if it's oriented properly, will interact. And that is relative to other dipole-dipole interactions, that's the strongest one. Now, it doesn't have to be an oxygen to hydrogen bond. It can be fluorine, which is even more electronegative than oxygen. Nitrogen will also work. So NH will contribute to hydrogen bonding. Those are the only. I hesitate to say sulfur, but sometimes sulfur gets in there. I don't know if it's strong enough to be considered hydrogen bonding, but this definitely has a dipole towards sulfur. Right. Now, suppose we're talking about molecules that are symmetrical. That is, either they may have polar bonds, but the symmetrical arrangement of those polar bonds they all cancel each other out. Like for carbon tetrachloride, right? What's the geometric shape of carbon tetrachloride? Well, we could go through the procedure and use the VSEPR model and determine that carbon tetrachloride is a tetrahedron with chlorines at the apex of the tetrahedron. Right? Carbon in the middle, right? So the bonds are actually here, 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 and here. And even though those bonds are polar, the molecule is nonpolar because all of the polarities cancel one another out. So the whole molecule is nonpolar. Well, let's go one step further. What if all the members of the molecule are equal or very close in electronegativities? Then the bonds are nonpolar and the whole molecule is nonpolar. And we could use something like nitrogen. Right? There's no polarity there. But what do we know about nitrogen? Well, nitrogen's a gas at room temperature and pressure, right? 1 atmosphere pressure. But if you compress and cool it, eventually it condenses into a gas, liquid. So when does that happen? Well, minus 195 degrees C. So you got to get it really cold. But if there were no, if dipole interactions were the only thing going, then it would never condense, right? There's no possibility for dipole attractions there. But the evidence says that there are forces there. Otherwise, it would not condense into a liquid. There'd be nothing to hold it together. Now, why does it take that cold temperature? Because above that temperature, the kinetic energy of the molecules is so high that the forces that would draw them together are broken instantly. The forces of attraction are too weak to be effective or felt by the molecules until you reduce their kinetic energy down below that temperature. So I may have said it before, I'll say it again. Nature, it just does what it does. It could care less what we say about it. All of these theories, laws, explanations that we apply to nature are there so that we can wrap our brains around it, try to understand it. But nature just does what it does. You'll also see evidence of these weak forces in things like noble gases, like xenon. I don't remember the temperature at which it condenses, but it's very low. But that's just a single atom. You know, how do you get attractive forces out of a single atom? Well, as it turns out, the problem was investigated and explained. And at least credit was given to a fellow by the name of London. We call them London dispersion forces. And the reason we put dispersion in there is because electron density is unequally dispersed over an atom or a molecule that has no other forces available to it. In other words, there's no dipoles there, no ions, no covalent bonding. The only thing left is extremely weak. I mean, dipole is weak, but London dispersion forces are orders of magnitude weaker. So how do you explain London dispersion forces? Well, they're not a permanent redistribution of electron density. They're an instantaneous redistribution of electron density. So in a microsecond, you can have that. Just for an instant is all it takes. Or on this atom, xenon is a very large atom. And in fact, London dispersion forces are more pronounced in large atoms because they have more microstates that are possible. Remember that? Well, we haven't got there yet, excuse me. I'm using a term that I haven't defined yet. There's more room for electron movement. So it's more likely with large atoms like this to get distribution of electron density moving around in more different places. So you could get something like this, right, around that atom. And the evidence for that is condensation from gas to liquid. It wouldn't happen if there were some forces, if there weren't forces there. Okay, so what does this have to do with the attractive forces? Well, let's say we have pure nitrogen. That's it. Let's keep it simple. If this nitrogen atom encounters another nitrogen molecule, excuse me, I misspoke. Nitrogen molecule, it encounters one that looks like this, and it, for that split second, has paused and it's neutral throughout. Then what this does is it repels electrons from its neighbor. So this becomes, and they move over here, where they are attracted by that one. There you get your attractive forces. That, in a nutshell, is London dispersion forces. Okay, I took a long time on this one slide, but the subsequent slides are just more detail on the same thing, so we'll probably skip over them. All right, there's what water looks like with its hydrogen bonding. Intramolecular bonds are always stronger. And there's the explanation in a sentence. Phase changes in general from solid to liquid and liquid to gas are explanations for these intermolecular forces. We know that the gases take up a lot of room, right? How do we know that? How do we know that a gas is the molecules are farther apart and take up more space than they do for liquids or solids? Density, right? We can measure density. The density of gas is very low. In other words, mass per unit volume. So if the mass is the same across this spectrum from gas, liquid, solid, we can establish that mass and keep it constant. Then what changes? If the density changes, then the volume has to change, right? And where does the volume come from? The mass comes from the number of molecules, and we didn't change that. So the only thing that can change volume is the space in between them. Okay. So what accounts for phase changes? Well, remember, we always have these forces acting between molecules, the intermolecular forces. And if the kinetic energy of the molecules is low enough, then they're not moving, they're not vibrating, they're not moving fast enough to overcome those forces. So they're holding them together. In a solid, they hold them together in a definite shape and a definite volume. But if we add a little energy and get them vibrating really fast, eventually they'll break those bonds, and then they'll start sliding past one another. That makes a liquid. If we add enough energy, then we break all interaction between the molecules and they just fly apart. And because we've broken those bonds that are holding them together, which the same bonds that make a solid are still occasionally experienced in a liquid, then that substance, those bonds are still working. But if we break those bonds completely, we get a gas. So what does that say about the amount of energy required to do it? Well, to go from solid to liquid, there's a certain amount of energy, right? Let's say that's 1. The amount of energy to go from liquid to gas is like 100. It's a huge amount compared to melting. Now here's density. I talked about density earlier. Of course, water is a bad example, right? Because you would expect density to decrease going from a solid to a liquid because the molecules are moving farther apart, right? But in fact, when we go from solid to liquid, the density is increasing. It's like the the water molecules are getting closer together. And I can explain it, of course. But first I'll point out that going from liquid to gas, notice the huge difference in density, 4 orders of magnitude. All right, how do we explain less dense solid than liquid? Well, for water, it has to do with the arrangement. It's still hydrogen bonding involved, but it's the arrangement of molecules in the crystal of the solid. When water is a liquid, you've got the water molecules moving past one another, and they can get as close or as far apart as they want, depending on the amount of energy available. But when we start to form a solid, we form a hexagonal network of water molecules. So you might have an oxygen here, and you have a hydrogen here, and an oxygen there, right? And then down here, another hydrogen, oxygen, 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 oxygen. And then we would have a hydrogen over here, and then a hydrogen, hydrogen over here, attached to an oxygen. So they form this regular hexagonal structure, and anytime you look at a snowflake, you know what the shape is, right? 6 points. So what does that do? Well, it creates a lot of empty space in there, right? We're increasing the volume, density goes down. Okay, there's some more talk about dipole forces. I've already mentioned those. We quantify it here. Dipoles are about 1% as strong as covalent or ionic, if you take them as a group. Covalent is stronger than ionic, but taken all together in a rough estimate, dipole is about 1% the strength of either of these. Hydrogen bonding, of course, is stronger. It involves hydrogen and some electronegative atom like nitrogen, oxygen, or fluorine. London dispersion forces. This is a key point right here. All molecules experience London dispersion forces. In other words, there's instantaneous redistribution of electron density. In molecules that have dipoles, the redistribution is minor. And the forces that are involved in London dispersion are so small that they're insignificant compared to the London dispersion forces. Just like dipole interactions are insignificant compared to covalent bonds. But they're always there. Okay. So I started talking about melting and boiling points earlier. And you can make a generalization about melting and boiling points based on the strength of the intermolecular forces. So if you can identify, and remember, these melting and boiling points, they're physical properties of substances. Nothing about the molecule, about the nature and the identity of the molecule changes. The stronger the intermolecular forces, the higher the melting point, the higher the boiling point. So a case in point, water. If water were a symmetrical molecule and the dipoles cancel one another out, all the water on this planet would be a gas at these temperatures and pressures. There'd be no liquid water on the planet. But since the molecule does have a dipole, the forces are strong enough to hold it together and increase the freezing point to 0 degrees centigrade and the boiling point to 100 degrees centigrade. If it were not for the dipole of water, those values would be much, much, much lower. They'd be more like methane. Okay, so we have trends that we can talk about. So here's the boiling points, right? And we can say, all right, so what if we have, let's look at this vertical line first. Stay in period 2. All right, so here's period 2, starting with lithium. So let me get this centered. There we go. Going across, and we have, at this point, we're at carbon, nitrogen, oxygen, and fluorine. So we would expect that as the electronegative difference between the central atom and the hydrogen, as that increased from left to right, we would expect that the dipole to increase and the boiling point to increase. Okay? So if we go from carbon to nitrogen, we find that the boiling point does increase. Right? If we go from nitrogen to oxygen, we find that the boiling point does increase. But if we go from oxygen to fluorine, we find the boiling point decreases. So that's an anomaly that requires an explanation. So why is that? Well, the first thing we can infer is that the dipole moment of that molecule, HF, is less than the one for water. Okay? Now, how do we explain that? Well, one explanation that comes to mind is HF is like that. So we're going to get a dipole moment this way. Whereas water is like this, and we get a dipole moment this way for the whole molecule. But there are no unpaired electrons in this molecule right here. But water has 2 pairs of unused electrons, which means the electron density is shifted even further that direction, which makes the dipole moment stronger. That's just one explanation that comes to mind. So it's not just electronegativity, although for the most part it is. Now let's look at, let's stay with carbon and go in a group rather than staying in the period. Let's start with carbon and move down the group. Right? So carbon, silicon, germanium, tin. What kind of trend would we get there? Well, actually what we get there is symmetrical molecule. So the whole molecule has no dipole moment. But what we find is that the trend is as the central atom gets larger, since the whole molecule has no dipole, right? We've established that they're symmetrical. Not only is the, well, actually going from carbon up through tin, the electronegativity difference should be decrease. So that doesn't explain why the boiling point increases. We're actually getting a stronger intermolecular force as we increase from carbon to tin. So there has to be a different explanation, right? Electronegativity can't do it because it should be the other way around. So what's happening? Well, since all these molecules are nonpolar, what we're seeing is a difference in London dispersion forces. Remember what I said about xenon? The larger the atom, the stronger the London dispersion forces can be. So we go from a small carbon atom in the center, which makes a small molecule, and then the molecule gets bigger for silicon because we're moving down, right? We've added another energy level. So silicon tetrahydride gets bigger. London dispersion forces are increasing. Germanium, bigger. Tin, even bigger. So 10 tetrahydride is a huge molecule compared to methane, and that means London dispersion forces are stronger. Now, we get that trend for the other series as well, the other groups. The one with phosphorus, this one with halogens, and this one with the chalcogens. Now, the problem is the trend breaks, right? The trend from here up, we can explain that with London dispersion forces and electronegativities. But when we get to this period, what we would expect here for water, if we follow this line, water should be down here. But what we get is a massive increase in dipole for water, hydrogen bonding, which destroys the trend. Okay, so I probably beat that horse enough. It's already dead. The key is to try to balance what are the forces doing and make them match what nature is telling you. This data, I mean, that's, you can't argue with it. I mean, it's true. So what we have to do is shift our thinking and decide what forces are predominant to explain the data. Okay. Little concept check. Which molecule is capable of forming stronger intermolecular forces? Well, that should be obvious. The one that has dipole-dipole versus the other that only has London dispersion. Right? So there's your explanation. Now suppose we have a molecular formula, right? We've determined this molecular formula the way we did in the first semester with our analytical techniques and deducing from the data what's the empirical formula and then what's the molecular formula. So we've got it right here. But we don't know anything about the structure. One way to determine, decide between two possibilities, there's probably more than one possibility, but say we proposed this structure, which is C2, AH6, O, or C2, AH6, O, right? Same molecular formula, but different structure. Well, if you compare the boiling points, which one should have the higher boiling point? The one that has the stronger intermolecular forces. Now, how do we deduce that? Well, we look for possibility. We know London dispersion forces are there, right? That's a given. But are there any dipoles available? Well, look here. We've got a hydrogen bonding potential right here on the end of the molecule, right? So that's going to be a pretty strong dipole interaction among these different, among the same molecules. But over here, what do we have? Well, we have oxygen against carbon. So we do have a little distribution here toward oxygen, right? So there's potential, but any dipole on these two bonds is canceled out. Now this molecule, of course, is going to be bent because we have these lone pair electrons. So there's going to be some potential for dipole, but it's not nearly as strong as for this one. This molecule is ethanol, the drinking kind, right? This molecule is dimethyl ether. And we know that the boiling point of ethanol is, let me see, what is it? It's a neighborhood of 78 degrees Celsius. And ether is, I don't even know what the boiling point for ether is. You know, if you open a bottle of ether, you're going to smell it across the room like that. It has very high vapor pressure. It just comes out of that bottle and across the room. You open a jug of crystal clear, and you may not ever smell it across the room. Right? Everybody knows what ethanol smells like. So we know from evidence, the boiling point evidence, that the intermolecular forces for this molecule are much stronger than they are for that molecule. All right, which gas would behave more ideally? All right, look at the question. All right, the same conditions of pressure and temperature. All right, we've got those locked. Whatever they happen to be, they don't move. So under those conditions, which one behaves more ideally? Well, we have to define what do we mean by ideal. Go back to the kinetic molecular theory. That defines ideal behavior in a gas. So what do we say about an ideal gas? It never condenses. It's always a gas forever, no matter how cold or how high the pressure. Which means that there are no intermolecular forces. They don't interact. Well, which one is more ideal, right? We already know that they're going to interact. We've already proven that up to this point. So which one behaves more ideally as the one with the weakest intermolecular forces? Right? So you look for a molecule where only London dispersion forces are available. Dinitrogen. Here you have slight difference, carbon monoxide, slight difference in electronegativity. The forces should be stronger among those molecules. So we find that the more ideal one is the one with the weaker intermolecular forces, dinitrogen, nitrogen gas. Okay, so how about states of matter? We've breached that subject already. Liquids have low compressibility. They're not rigid. They assume the shape of the vessel. And they have relatively high density compared to gases. Right? Low compressibility is under normal circumstances, that's true. Just think about hydraulic fluid, right? Why do we use hydraulic fluid in systems? Because when you apply a force from one end, it's transferred instantly to the other end. It doesn't absorb any of that energy in compressing the liquid. Those are at levels of compression and force that are right here. If you go deep enough in the oceans, you get forces like that. And it's been shown that water at those depths does have an increased density. But those are extreme conditions, kind of like those are the Earth's black holes, right? They're extreme conditions. One other thing that liquids exhibit is surface tension. Surface tension is a force that resists pulling molecules apart. It's a tension, right? So that's also expressed in terms of an amount of liquid that has a surface, and it resists the increase of the surface area, like the surface of water in a bowl. Okay, there's your water in that bowl, and the size, the strength of the intermolecular forces contributes to an increase in surface tension. So how do we witness surface tension? Well, in nature, we have these little animals. We call them water skimmers. And you'll see them on still water, on a pond or in part of a creek that's leveled out and is not moving very much, maybe behind a rock. And you'll see these little guys just scurry across the surface of the water. Well, very few animals are less dense than water, right? If you take that little skimmer and submerge him, assuming there are no air bubbles attached, he'll sink. Well, so why does he float across the water? You'll notice that on all his feet, there are depressions in the surface of the water. Okay? The water is resisting an increase in surface area. So if you have a surface area that's here, this much, and over here, like that, that has more surface area than that does. Right? So his little feet, with the bug, his little feet are pushing down on the water, and the surface tension is resisting that change in surface area and pushing back. So as long as he doesn't exceed the amount of force required to break that surface tension, then he'll stay on top and he can just scurry around. You can also do that with a still beaker of water. You can take a needle, which we know is more dense than water, and very carefully, by the tips, set it on the surface of the water and move your fingers apart. And 9 times out of 10, it'll sit there right on the surface of the water. It'll be in a depression, right? Because it's applying force against the opposing force of surface tension. So there's some give. So why does that happen? Okay, here's the explanation. Water molecules throughout. Let's say there's nothing else. Let's just keep it simple. So you got water molecules here and here and here and here and here and here and here, here at the surface, there, right? So in the body of the water, they're equally attracted in all directions by their neighbors, right? But at the surface, the dipole, the dipole moment of water doesn't change. It's got to do something with those attractive forces. So it attracts this way and this way and this way. What does it do with that direction? Well, it redistributes that force to its closest neighbors. So that's where that extra force comes at the surface. And surface tension is just another piece of the puzzle, an evidence that intermolecular forces do exist and that they change based on the theoretical electronegativity, the dipole moment of the molecules. Here's another evidence. Capillary action. Capillary action, by definition, is the spontaneous rise of a liquid in a narrow tube. If you have a wide tube like this versus a narrow tube like that, there's your liquid. In this wide tube, let's say it forms a meniscus like this. But in this one, the water's going to rise up to maybe here. Now, why is that? Right? Well, there's a mass of water above the level, right? So here, of course, it would just be in equilibrium with the surrounding water, like this one. But this one, the water level, we're saying water here just to be simple. The water level rises up in that capillary tube. Now, what keeps it from going any higher? It's a balance of forces, right? Gravity is pulling that down. But there's something pulling it up, right? Capillary action, capillary force is pulling it up. So once it gets this high, then the mass of that water is counterbalanced by the force of the capillary action. Okay, so that's as high as it goes. And what we've noticed is the narrower the tube, the higher it goes. I submit that the force doesn't change. rise above this level in a narrower tube means that you get the same mass of water. But with a narrow tube, right, what's a cylinder? The area, the volume of a cylinder, consequently the mass of water, is proportional to the circumference. So a narrower circumference means you need a longer cylinder to get the same amount of water. But why does it do that? Okay, that's the interesting part. So let's take our narrow tube and blow it up so that we can see it better. But it's still narrow. Okay, so let's say we have a camera that will photograph 1,000,000 frames a second. So we can watch it. When we first put it in the water, we can watch it at the very beginning of the process and watch it move. Okay, so we start off here. And what happens is there's a competition between the forces of the water molecules to each other, cohesive forces, and they're also in competition with forces that attract water to the walls of the tube. Okay, cohesion versus adhesion. In the case of a capillary tube, the balance is in favor of adhesive forces, where the water is attracted to the walls of the tube. So in that instant, we get some of these water molecules rising up on the side, like that. They're attracted to the tube. But the cohesive forces, the surface tension, tends to draw that. It doesn't like, because there is surface tension in water, they don't like to be spread out that far. So they pull back again, and they pull back and pull the water up. So now you've got mass of water above the level, and you're still trying to balance the forces. So they're climbing up the walls, and you're rebalancing each time until you get to a certain level where the mass of that water now is balanced by the forces that are pulling it up. Can't go any higher. That's capillary action in a nutshell. Balanced, cohesive versus adhesive forces. Now, in a glass tube, why would water be attracted to the glass? Well, if you look at the surface of glass, right? Glass is basically, largely, a solution of silicon dioxide and other additives. So you've got silicon and then oxygen at the surface. Sometimes you have silicon at the surface, but you have enough oxygen there. And oxygen tends to be more electronegative. It's going to attract the hydrogens in the water molecule. So there you get your adhesive forces. All right. So what happens if the cohesive forces are stronger than the adhesive forces? In that case, you see, whereas water would form a concave meniscus in the tube because the adhesive forces are stronger than the cohesive forces. The other way around, the cohesive forces are stronger than the adhesive forces. You get a convex meniscus where, for instance, mercury tends to draw toward itself rather than with the tubing, the glass tubing in this case. Metal tubing wouldn't work because you couldn't see through it, right? So you can't tell. So we have to talk about it in terms of glass tubing. Now, that's a good thing actually for barometers, because if you used water in a barometer and the diameter was small enough, then you wouldn't just be reading air pressure in the barometer, you'd be reading capillary force as well, capillary pressure. So if you're going to use water in your barometer, you need a wide bore tube so that you minimize the adhesive forces. All right. So what is another effect, evidence of intermolecular forces? Viscosity. So what is viscosity? Viscosity of a liquid is the resistance to flow, right? High viscosity means the liquid flows very slowly, like Heinz ketchup from the bottle, right? Or honey from your dispenser. Large intermolecular forces means increased viscosity. So how do we change the viscosity of liquid? Well, the easiest way is to change the temperature. There are other ways, but temperature is a good example, because as we decrease the temperature, we're removing energy, kinetic energy from the liquid, and consequently, we're allowing the intermolecular forces to assert themselves. Okay? So if we take honey and stick it in the refrigerator, and then we pull it out, or molasses, or whatever your favorite sweet is, and we open the lid, turn it up, it just sits there, it won't move, right? It's almost a solid. It's a very viscous liquid. But if we heat it up, it will flow easily. Now, we were talking about liquids there. Talk about solids, okay? Solids can be subdivided into two types. Remember, nature does what it does, but this is to help us understand two types of solids. They're either amorphous solids, where there's a high degree of disorder in the structure, right? You can't see a regular arrangement of molecules in the solid. A perfect example of that is glass. Glass is an amorphous solid. In fact, some researchers claim that it's a supercooled liquid, but that's neither here nor there. And then there are solids that are crystalline in nature. In other words, they do have a regular structure, right? And the perfect example of that is diamond. Right? Diamond is a regular structure. In fact, a gemstone, a gem quality diamond that has no flaws in it is a single molecule. Now, another characteristic of these ordered structure crystalline solids is that we can describe them in terms of the unit cell. In other words, they have repeating structures. So this is the smallest structure that you can get that still represents that solid. And then all you have to do is just repeat it over and over and over again, and you still got that same crystalline solid. So that's the official definition of a unit cell. Three-dimensional repeating unit, okay? Now, we're going to approach crystalline solids from different directions. But remember, nature just does what it does. And these are different ways of explaining how those structures are arranged and the forces involved. Right? This is one way to explain it in terms of the unit cell. Another way to explain it is this closest packing structure. Remember, I've said it before, I know. I'll say it again. In nature, systems tend toward minimum energy. They tend toward stability. That means minimum energy. So the closer you can pack molecules into a regular structure, the happier they are, right? Happier. They have the lowest possible energy. So this closest packing structure is like one side of the coin, and unit cell is the other side of the coin. Right? Two different ways to explain this nature. They're related in some respects, and I'm not trying to make experts out of you guys, but I want you to appreciate the three-dimensional relationships and structures of solids. So we'll look at the unit cell first. Most crystalline solids are based upon some form of cube. Now, not all of them, of course. Most of the metals, yes. Pure metals, they tend to arrange themselves in some form of cubic structure. So when you see discussions of metals in terms of their crystalline structure, eventually they'll return to the cubic unit cell. And the most common unit cells are these three. The simple cube, right, where each atom, let's say of the metal, occupies a position at the corner of the cube. The body-centered cube still has these occupying those corners, plus there's one right in the center of the cube. Then there's the face-centered cube, where we have the corners occupied, and we have the faces of each of the 6 sides of this cube occupied by a member of the crystal. Now, this is the ball and stick model. In actuality, for this simple cube, those metal atoms are touching one another. They're definitely at the corners, but the closest packing says that they have to touch one another. Right? Now, with the body-centered cube, this central atom pushes them further apart, and they cannot contact one another. So there's a gap there. And then with the face-centered cube, you get some contact, but the cube corners do not contact one another. Okay, so that's, and these regular cubic units can be placed into a lattice where you have the regular repeating unit over and over and over and over again. Okay, let's see, there was one other thing I wanted to say about this. We're going to cover it later. Okay, so hold that in the back, and I'm going to talk about a method for determining the spacing between molecules. Like here, notice with this lattice, notice that you've got a layer of atoms here, and then you got another layer of atoms in the middle and another layer of atoms in the bottom. Okay? So we know that if you try to pass light of a certain frequency through that crystal, the wave nature of light will cause interference. Sometimes it's negative interference, where the peaks of one wave meet the trough of another and they cancel out. That's destructive interference. Sometimes you get the peaks of neighboring waves matching one another, and that's constructive interference. Increase the strength of the signal that you detect on the other side of the crystal. If you aim X-rays of a known wavelength at the crystal at the right angle, it won't go through the crystal, it will go in, interact, and come out. Okay? And when it comes out the other side, if there has been constructive interference, the signal will be increased from where it would be. You know, some of it is absorbed in the crystal, so you're looking for a relative peak of energy. So that's what the Bragg equation does for us. There's your wavelength of the X-rays. Now, why do we use X-rays? Because if we use longer wave light, it would just pass right through the crystal and not interact at all. It has to be, the wavelength has to be comparable to the size of the atoms and the distance between them. So that's why we have to use X-rays. Now here's the distance between the atoms, right? And here's the angle of incidence and reflection. Remember, I don't know if any of you have had physics, but there's your reflector. And if you have a light beam coming in, then it's going to bounce off at the same angle, right? So if you have a vertical, the angle of incidence is right here, and the angle of reflection is right there. And those two are always equal. Okay? So we know the angle of incidence because we set it. Right? It's fixed. And then we move, well, actually, you move both of them. And when you get a peak, an increase of energy coming out the other side, then we know that the light has been effectively reflected from the crystal structure. That only happens at certain wavelengths. And there may be multiple places where that happens as you move that angle, change the angle. And that's what the N is for. At one end, you get a certain, that angle, you get a certain angle, and then you keep moving it. At N equals 2, you get another angle. N equals 3, you get another angle. So here's why it works. So here's your layer of atoms, and here's the second layer of atoms. So you get one wavelength coming in, and why does it bounce off the surface, or why does it interact with the surface? It interacts with the surface because of atoms, right? And there are electrons surrounding them. So there's an interaction there. So when it bounces off this surface at a given angle, and this light beam comes in at the same angle, you get a reinforcement. Notice that the peaks and the troughs match. When that happens, then we know that this distance can be calculated, right? So we determine this angle. We know the wavelength. The N varies, right? And then we have D, which is the distance, and usually that's what you're calculating for. All right, so that was just 2 dimensions. Actually, 1 dimension, where you do that's 2 dimensions when you do an angle. Sorry. But we can use this technique. It's a little more complicated, but we can use it to tease out information about the crystal structure in 3 dimensions. It takes more work, and before supercomputers, it took a lot of man hours to figure it out. But if you have your crystal down here and you shine X-rays into it, it will produce what's called a diffraction pattern on a detector or a film. And then you build up evidence over years of different types of crystals, so you know what a regular crystal looks like. If it's this type, it'll give this type of pattern and so forth. And then you get down into the gritty of the individual differences of crystals. In fact, this is how the double helix of DNA was elucidated. It took a lot of actually woman hours. The woman that was responsible for this process worked for Watson and Crick, only they got credit and the Nobel Prize and she didn't. But of course, by the time they got the prize, she had passed away. She had developed some kind of cancer and died very young. But she was never officially given credit. Anyway, they used these diffraction patterns to elucidate the structure of the double helix. The real problem was you have to get the DNA molecule into a crystal structure. It's got to be regular, right, before you can use this procedure. And that was really the first big hurdle they had to overcome, because large molecules like that are messy. They don't like to form regular crystals. Okay. So, crystalline solids can be formed from various types of components. They can be ionic solids, right? So in an ionic solid, one of those positions, say in the cube, would be occupied by a cation, and the neighboring position would be occupied by an anion. And the cation would be surrounded by anions and vice versa. Those are ionic solids. Molecular solids would form from pure molecules. For instance, ice, water ice would be a molecular solid. Or let's see, what's another good example? Nothing comes to mind right now. Atomic solids, particularly those made with metals, are individual atoms in the lattice. Now, they can be homogeneous with one type of atom, single element, or you can mix in various atoms. And that will usually change the structure of the crystal solid, of the atomic solid. And engineers have been using this process for hundreds of years to modify the behavior of things like iron, right? Pure iron is very soft. I mean, you can peel it up with your fingernail. But if you mix some or copper, for instance, right? Let's go back even further. Before the Iron Age, we had the between the Stone Age and the Iron Age, we had the Copper Age. Utensils and weapons were made out of copper. Well, some bright soul figured out that if you mixed a different metal in there with the copper, you could make it harder. We changed the crystal structure of the atomic solid by mixing some tin in with the copper and make bronze, which is a stronger alloy. Okay, so crystalline solids can be subdivided into ionic, molecular, or atomic. Examples, all right? There's diamond, sodium chloride, of course, would be the ionic one, right? Ice would be the molecular one, and the atomic one would be diamond. And those are formed from covalent bonds, right? The forces holding them together, in fact, are beyond dipole. These covalent forces are very strong. Consequently, diamond is the hardest naturally occurring substance on Earth. Sodium chloride, those are ionic bonds holding those parts of the solid together. And of course, hydrogen bonding, dipole-dipole, is holding the molecular solid together, composed of water. Okay, this is just a chart taken straight out of your book, a table. that gives you an overview of atomic, molecular, and ionic solids. Now, within the atomic solids, you can have different types of bonding characterizing the solid. In the case of diamond, of course, you have nonmetal atoms, and they're covalently bound. In fact, in one single giant molecule. Whereas with the metallics, you get what is often described as a delocalized covalent bond. It's a metallic bond. It's a special class of bond. And the molecular orbital theory accommodates the metallic bonds very well. Whereas 8A, what's 8A group? Right? Noble gases. The only thing holding an atomic solid made of noble gases is London dispersion forces. Right? So you have these three different classes of forces holding atomic solids in their crystal structure. Molecular solids, of course, they're discrete molecules, so the only thing you've got available to you is dipole-dipole or London dispersion forces. And then ionic solids, of course, they're individual ions, and they attract one another with electrostatic charge. Okay, now for the flip side of the coin, closest packing model. And we're going to use an example of the metal atoms, right? They seem to work best with this and easiest to describe and understand. We have to make some assumptions, of course. The metal atoms are uniform in size, and they're just hard spheres. So that's our starting point. And then we pack them in layers. Let's see. Now I've got this video that'll help describe it, but you have to tune your ear to the Indian accent. And it takes a minute to load. So just be patient. It'll come up. If I can be patient. Nope, wrong way. Sorry. Fold our hands and wait. There it goes. May have to turn up your volume a little bit. It's a nice Indian name, Sanka.
Constituent particles in a crystal may be thought of as solid spheres. In this video, we shall try to understand the close packing of spheres in a 2D space, leaving minimum vacant space. Packing in one dimension. There is only one possible linear one-dimensional arrangement possible with spheres. They queue up linearly, each sphere touching the adjacent spheres like this. Packing in two dimensions. To arrange spheres in two dimensions, we take the linear one-dimensional arrangement that was shown previously. There are two ways by which we may arrange the spheres in a two-dimensional platform. They may be arranged like this. Note that each linear arrangement are aligned vertically. Here, the vacant space is this. Now, in this packing, the spheres take up only 52.48% of their relative space. Here, a single sphere touches four other spheres. If we join the centers of the spheres, we get a square. Therefore, this packing is called square closed packing. A second way of arranging the linear one-dimensional arrangements is to keep the spheres in the second linear one-dimensional arrangement in the depressions of the first, like this, where every alternate linear arrangement has the same alignment. These are the vacant spaces, which is visibly less than the square closed packing and hence more efficiently packed. In this packing, the spheres occupy 60.4% of the available space. The voids created in this packing touches three spheres forming an equilateral triangle and are called triangular voids. A single sphere touches six other spheres, and by joining the centers of these spheres, we get a hexagon. Therefore, this packing is called hexagonal closed packing. Packing in 3 dimensions. Taking square close packed 2-dimensional layers. This is done by placing a 2-dimensional layer just above the first layer and so on. All the layers are vertically aligned. Taking hexagonal close packing 2-dimensional layer. The first layer contains red colored spheres indicating the alignment of the layer. This alignment is called A. These are the void spaces of the layer. We have to place a layer on top of this layer. For efficient packing, we will have to place the second layer in such a way that the spheres are exactly over the triangular voids of the first layer. Only these triangular voids can be covered. The spheres of the second layer are blue in color, which indicate that this layer has different alignment and this alignment is called B. We can no longer see all the void spaces created between the two layers. In order to overcome this problem, we will make the second layer transparent. Now we can clearly see the two different types of voids created by these two layers. These are called tetrahedral voids, marked by the letter T, and these are called octahedral voids, marked by the letter O. The tetrahedral voids are created by 4 steps. First, we make the spheres a bit smaller in order to understand the shape. Then we join the center of the spheres by straight lines. The shape is a regular tetrahedron. So the void is called tetrahedral. The octahedral voids are created by 6 spheres. Here also we make the spheres a little smaller, then join the center of the spheres to get the shape. The shape is a regular octahedron. Placing the third layer. This can be done in 2 ways. These are the triangular voids of the second layer that are not involved in making octahedral voids with the first layer. By placing the third layer above these voids is one way of placing the third layer. If we do this, we can see that the first and the third layer have the same alignment A. With similar reasoning, we keep a fourth layer on top of the third layer and see that the second and fourth layer have the same alignment B. This pattern of close packing is called ABAB type pattern. We make spheres a little smaller and join the center with straight lines to understand the shape. It is my belief that this is the unit cell of this close packing because it is the smallest unit that may be repeated on the entire crystal. The top of this unit cell has the shape of a rhombus having gamma equal to 120 degrees. 3 such rhombus form a hexagon. For better visual cognizance, this shape is taken as the unit cell of this close packing, which is called hexagonal close pack or simply HCP structure. Another way of placing the third layer is to cover the octahedral voids of the second layer by placing the spheres of the third layer above the octahedral voids made by the first 2 layers. The alignment of the third layer is different from the first 2 layers, and so the color of the spheres have a different color, that is green color. Let this alignment be called C. Using the same reason, we can cover the octahedral voids created by the second and third layers by a fourth layer. It will be found that the fourth layer has the same alignment as the first layer. So this pattern is called ABCA type pattern. Now again, making the spheres a little smaller and joining their centers by straight lines, we get the shape of this packing like this. The unit cell of such a packing is this. This is nothing but a face-centered cubic lattice. So this type of packing is called cubic close pack or simply CCP or even FCC structure.
So this video, I hope, was sort of dovetailing those two sides of the coin, the close packing model versus the cubic. And they did meet occasionally. And on the surface, it looks extremely complex. And it can be. But if you understand the progression from linear to two-dimensional to three-dimensional, and that for the most part, we have two types of stacking that can occur, right? You can have the ABAB or the ABCA type packing. Then we have a common language. We can talk to one another about it. And now these are slides that discuss that and reinforce the fact that in hexagonal close packing, we have the hexagonal unit cell. So the hexagonal closest packing doesn't have a cubic form. That doesn't mean that cubic forms don't exist, but they don't overlap. They only overlap with the face-centered cube in the ABCA version. So here we have the ABCA, and there you have the cubic close packing or face-centered cube can be traced to this other side of the coin. Okay, and hopefully this will also describe what type of, actually there is a connection between the hexagonal closest packing and the cubic unit cell. So if we take this example, and there it is in its stacking, the ABA, and then we looked at the layers and the atoms that are, or molecules as the case may be, as they touch one another, we find that we can also describe this unit cell in terms of the face-centered cube. Okay, so that's saying, okay, now they're confusing me. Cubic closest packing versus hexagonal closest packing. I think what the authors are saying here is that both of them can be described in terms of face-centered cube. Be that as it may, since I'm not trying to make experts out of everybody, we look at the nearest neighbors. So you pick an atom and you look at who's touching it, right? For the cubic closest packing and the let's back up, and the hexagonal closest packing, we have a coordination number of 12, which means that this one that we focus on here, this red one, is in contact with 12 other atoms. So that's what coordination number means. So suppose we go back to the cubic unit cells and we look at the simple cube, body-centered cube, and the face-centered cube. This one is going to take us through the face-centered cube. So what are the net number of spheres or atoms, as the case may be, in the cubic unit? How many atoms can it claim for itself? Okay. So we look at this one as our example, and we say, all right, so this unit cell is in contact with these other atoms and cells, so that means that it can only claim those that are within the cube, right? So these corners, there's only 1/8 of an atom in that unit cell. And for the face-centered, there's only a half a cell, right? So how many faces do we have on a cube? Well, think of a rolling the die, right? It has 6, you can have 6 numbers, 6 faces on a cube. So 6 times a half is 3. So the faces can account for 3 atoms in that unit cell. Whereas the corners have how many? Well, they're 1/8 of an atom, but there are 8 of them. So there's only 1 there. So that means the face-centered cube accounts for 8. A total of 4. Excuse me, I misspoke, 8. A total of 4 atoms in the face-centered cube. A simple cube is how many? Well, there's 1/8 times 8 is 1. So the simple cube can only claim 1 atom per cube. Face-centered, we did that one already. How about the body-centered? It's not showing the body-centered. All right, let's draw the body-centered. So you have a cube. Okay. And we have all the corners occupied, but we have 1 in the middle. So how many are claimed here? 8 times 1/8 is 1, plus we got 1 in the center. So a body-centered cube is only 2 atoms. So a simple cube is 1, a body-centered is 2, and a face-centered is 4 atoms per unit cell. Okay, so how can we use that information? Well, perhaps we want to know something about the density of a metal, say. We can measure the mass, but we need to know how many unit cells are in there and what their volume is. So we need to know something about the unit cell. Is it a cube? Is it a body-centered? Is it a face-centered? And then once we know the number of atoms that are attributed to the cube, then we need to know the volume of the cube, right? And in order to know the volume of the cube, you need to know something about the atoms that are in it. So for a simple cube, the length of the edge of that cube is related to the radius of the atoms by this formula. 2 radii is the edge of a cube, right? See, is it going to show me a picture? No, it's not. Remember, when we had a simple cube, the atoms touch one another, right? Like that. So here's the edge of the cube, and there's one radius, and there's the other radius. So 2 times the radius of the atom gives you the edge of the cube, and you can find the volume of the cube. You know the volume of the cube? You know how many atoms are involved? So all you need to know is something about the atom. What element is it? Right? And then you can calculate the density. Similarly, with a face-centered cube, the length of the edge of that cube is the radius of the atom times square root of 8. And for a body-centered cube, the length of the edge is the radius of the atom times 4 divided by the square root of 3. Now, I'm not going to go into the geometry here and the trigonometry, but believe me, it's there, and I can get you the information if you want, if you're interested in more detail. I think I still have documents written up. I was interested enough to create the document myself. Okay, so here's an example. Say we have silver metal and we want to calculate the density of it. We need to know something about the structure. It is cubic closest packing structure, which means a face-centered cube, right? And the edge of the cell is 409 picometers. right? We could have deduced that edge of the cell. All we needed to know was something about the radius of the silver metal atom, right? So we could have got that. We just said face-centered cube, cubic closest packing, and it's silver. That's all the information you need if you dig for the other resources. But this is given to us, so we'll go with it. So what is the measured density of silver? Right? It's measured at 10.5 grams per cubic centimeter, right? So what if we calculated from this information? What would that look like? Well, we know that the face-centered cube is 4 silver atoms per unit cell. So with 4 atoms, we can calculate their mass because we know the molar mass of silver. So that's a simple calculation. Then we need to know the volume, right? Mass divided by volume is density. So we can calculate the mass because we know how many atoms are in that volume. Now we need to know what's the volume. Well, if this is the cell edge, then the volume is going to be the edge cubed, right? Because it's a regular solid, same length on every height, width, depth, are all the same. So it's just cube that value. But we need that, this is in picometers, we need it in terms of cubic centimeters. So we have to do unit conversions. And that's what this step says to do. Then we just take the 4 atoms, their molar mass, do a unit conversion there with the moles per atoms, and we find out that we calculate the density to be 10.5 grams per cubic centimeter. So we arrived at the same answer from 2 different angles. One direct measurement here, calculated. So how do we explain? I mentioned a little earlier, bonding models for metals. Theories concerning how metals bond have progressed over the years, and they usually start simple and they become more complex. And then what do you do with a theory when it fails to describe? You either throw it out and start over, you modify it, or you restrict its application. So the electron C model has very limited application. So for all intents and purposes, we threw it out. And now the band model, which is a subset of the molecular orbital model, is better at explaining how metals bond to one another. Right? This was the C model. You just had cations and a sea of electrons. And they just exchanged those electrons, and you couldn't tell who belonged to who, so they say, okay, we're fighting over them, and that draws them together. And electrostatic forces among the electrons and the cations as a partial explanation for how metals bond to one another. But for the molecular orbital model, the band model, the electrons are assumed to travel around the metal, right? But remember, the molecular orbital model takes the entire substance, however much you have, and it takes all the atomic orbitals in the valence shells and mixes them together, and it makes a set of molecular orbitals. Okay? And those molecular orbitals then are filled with electrons. Well, if you only have 2 atoms, then you get their valence electron atomic orbitals mixed together to form a couple or 4, or however the case may be, of molecular orbitals that are pretty far apart. So just those 2 atoms wouldn't explain in themselves how you get high electrical conductivity and high thermal conductivity in metals, because that means that with just a little bit of push from one side, you spit electrons out the other side. So that means that the jump from one atom to the next through these molecular orbitals has to be very narrow. So if we say take a mole of atoms, so here's 2, 4, the more atoms you take, the closer together those energy levels get. So once you get to a mole of atoms, and for silver that would be about 108 grams of silver, you would have a mole of atoms. Then the spacing between the molecular orbitals is so close together that they just need a tiny push and the electrons travel from one to the next and out the other side. So high electrical conductivity, high thermal conductivity are easily explained by the molecular orbital model for metals. I'm not going to spend a lot of time on those. I want to talk about alloys. I mentioned earlier bronze, where we changed the structure of the crystal structure of the metal by inserting a different metal in place of copper. In that case, we used tin to make bronze. Well, what we were making was an alloy. And a metal alloy is a solution of metals. But you can have two types of alloys. Right? Suppose you have a structure of metals here. And these are all copper. But we want to make an alloy. So we take one of these and we substitute tin. That makes bronze. If you put a certain number in there. That's called substitutional alloy, where you actually replace one of the atoms in your structure, in your crystal structure, with a different element, a different atom. Substitutional alloy. There's a replacement. Interstitial alloys, on the other hand, remember when the author, the narrator in that video was describing the voids, right? You have different types of voids in the packing. Well, if the atom is small enough, you can stick it in a void, right? And that's what steel does. So steel has these iron atoms, and there are voids right in here. Like that. Those little voids, I know I drew it too small. But inside those voids, you stick carbon atoms. And the carbon atoms are small enough to fit in those voids. What does that do to the crystal structure of iron? What it does is it actually changes the way that those atoms interact. It changes the crystal structure. And the way it does it is, it keeps those iron atoms from sliding past one another. Because that's what they will do. If it's pure iron, you can scratch it with your fingernail, which means they're not held together very strongly. But if you stick a carbon atom in there, say 0.5% by mass or less, will give you steel. 0.2 to 0.5% is considered high carbon steel. Anything less than that is low carbon. And that locks those layers in place, it's harder to move them. So that's what hardens iron into steel. That is an interstitial alloy. The interstices, or the voids, are where you put your alloying materials. Another example, brass, right? Where you put zinc in there for copper, or you put, and this is an interstitial, Another example is with steel. You can have those carbons in there, but you can substitute for the iron chromium. And if you put 11% chromium or greater, originally it was 35%, you get stainless steel. And now you're not just changing the structure of the steel, which makes it harder, but it also changes the corrosive properties of steel. Because chromium is much more reactive than iron in an oxygen atmosphere. So on the surface of the stainless steel, the chromium atoms react with oxygen from the air. And they form a skin on the layer, on the surface. So much, very quickly, so quickly that if you scratch the surface, it immediately repairs. And the rusting or corrosion of the iron does not proceed. It makes the metal extremely hard. In fact, metal workers don't like to use stainless steel unless they have to, because it's so difficult to work with.
Dr. Bly, I have a question.
Yes.
Can an alloy ever occur naturally? I
Oh,
didn't
yeah.
know if that was a dumb question or not. I didn't know.
Oh, no. No, that they do occur naturally. I can't think of an example off the top of my head, but I know they do occur. And in fact, when they do occur like that, that's where the technology of smelting is involved to separate them. If you need pure substances, actually smelting is more closely related to oxides of the metals, because most metals in the crust of the Earth occur as in compounds.
Okay.
And many of them are oxides, particularly iron ore is iron oxide, and bauxite for aluminum is aluminum oxide. But the alloys, I'm sure they do occur. Gold, of course, you're more likely to find gold as individual nuggets, but you can form alloys even with the gold nuggets, right? As they're purified and deposited in various veins in minerals, they will pick up atoms from those minerals and deposit in their interior. So even though the gold nugget might be, I don't know, 95% pure, it'll still have alloyed elements in there with it. Okay, so that's alloys. We can look at network solids like diamond, and they occur in different forms, allotropes. So one allotrope of carbon is diamond. So the regular structure here is tetrahedral. But carbon can also occur as graphite. So the covalent bonding in diamond is amongst all of the carbon atoms, very strong. With graphite, you only have covalent bonds in this layer. So the hexagonal layers of carbon atoms interact with one another through weaker intermolecular forces. And since they have to be I'm reverting. They have to be London dispersion forces because there's no electrostatic difference. There's no dipole here. So that's why graphite is used as a dry lubricant, because the layers slide past one another, but they're not wet. They're not liquid, they're not oily, they're not moisture prone. So you still get the lubricating effect, right? So your parts can slide past one another because the graphite is between them, but they don't pick up dust, oil, water, whatever. So it makes a very good dry lubricant. In fact, I used to carry a squeeze can with graphite in it in a long, narrow tube when I was a biker, dirt biker. And you would just loosen up the cable. Actually, you wouldn't loosen it at all. You just find the gap, stick that little tube in there, and you squirt your graphite into your cable, and it would lubricate your cable through the guide. Now, diamond, as a consequence of the molecular orbital theory and the energies that are described, right? Because molecular orbitals can be used for carbon atoms as well. In diamond, the molecular orbitals that have electrons in them and those that don't, there's a very wide energy gap, right? So these electrons are bound very tightly in those bonds. So as a consequence, as opposed to metals, where the difference between the energy layers is very narrow, diamond is an insulator, both electrical and thermal. So gemologists use that property to determine if the gem that they're being asked to appraise is a diamond. All they have to do is take this device and touch it to the diamond, and it measures the thermal conductivity of the diamond. If it's very, very, very low, below a certain amount, then the instrument tells us that's a diamond. If it's higher than that value, then it's paste, it's fake. Okay, for graphite, this is just an illustration of the delocalization of electron density in the layers of graphite. Right? Not between the layers, but in the layers. That's what makes the layers strong. And they're overlapping p orbitals. Ceramics. What is a ceramic? Well, it's a solid. Yeah, it's a solid. It has crystal structure, right? But ceramics in general are operationally defined. In other words, a ceramic is what we say it is based on its properties. They're usually made of non-metallic materials, right? From this side of the table over here, non-metals. They're very strong, but they're brittle. They're not tough. They're strong but brittle. And they resist heat, transfer of heat, and attack from aggressive chemicals. So that being said, ceramics are a very useful class of compounds, class of solids. But usually they have to be backed by something that takes the stress from them. Because they're brittle, they need something that's not brittle behind them. So as a consequence, ceramics were used on the surface of the space shuttle because they were very strong and they were resistant to heat, which is good for a space shuttle coming back into the Earth's atmosphere. So as the heat of friction builds up on the surface, they just slough it off because it will not transfer across the brick into the space shuttle hull unless you get a break, right? If you get a break in one, then you run the risk of breaching the hull. So there were several layers, safety layers underneath the bricks. There was the adhesive that holds the brick onto the surface of the space shuttle. It was a very high temperature adhesive. So if there's just one brick missing, then it could withstand that and make it back to Earth safely. Now, of course, the leading edge of the wings and the tail and very, very high temperature areas was made of a special compound called advanced carbon-carbon. And it was even, I don't even think you would classify it as a ceramic. But that's another story. Most ceramics are made from clays, like china, stoneware. They start off with clay, and they try for a very pure, uniform particle-sized clay, either from deposits of that material or from artificially producing it in purification processes. Clays are basically silicates. Actually, they're aluminosilicates, but silicate, the silicon is the predominant member. And they are made ceramic by firing at high temperature. So you actually change the crystal structure of the material by building the clay into your shape and then firing it, and it holds that shape. It's very strong. We do that with, like I said, china, stoneware. That's the way bricks are made. So adobe structures that were typically used in the West to build housing structures had a limited life because they were not fired. They were just sun-dried. So the only thing holding them together was the straw that was mixed in with them. And they had to be repaired every year. As wind and erosion, rain, what little rain there was, would destroy them. But when you put brick as a facing on your house, it's been fired into a ceramic. So the bricks on the surface of my house are going to be there for hundreds of years. The only thing that may break down is what's holding them on the against the house. Okay. We can also get materials called semiconductors. Now, how does a semiconductor work? Well, let's start with conductors first. Conductors and insulators. A conductor is a material that will transmit electricity wholesale through its body with very little resistance. Whereas a resistor is just the opposite. It resists. Or no, an insulator, excuse me, not a resistor. An insulator versus a conductor. The insulator does not transfer electric charge across its body. So we combine conductors and insulators to make lamp cords or wiring for our houses. Well, between the conductor and the insulator, let's see, get both fists on the screen, is a class of compounds that are semiconductors. They conduct sometimes and other times they don't conduct. They're switchable. So that's the basis, the foundation of modern computer technology and electronics, is the judicious use of types of semiconductors. So how do you get a semiconductor? Well, first you need a pure substance, right? And preferably it'll be cheap and absolutely pure. I mean, 99.99999% pure. And it was discovered early on that silicon worked very well. There's lots of silicon everywhere. Sand on the beach, you know, just tons and tons and tons of it. The crust of the earth is chock full of silicon. So it's cheap. The real expense comes in purifying it. Right? So once you get pure silicon, then you do what they call doping it. So you change the crystal structure by, it's not really an alloy because it's not a metal, but you do replace some of the silicon atoms with other atoms. Okay, so if you have, let's say, I think I have a slide here. Yeah, we'll get to it. So an N-type semiconductor, N refers to negative, is you replace silicon with an element that lies to the right of it in the periodic table. So silicon's here, and if you replace it with phosphorus or arsenic, that means it has one extra valence electron. And that electron then is available for movement under the right conditions. So that's the N type. The P type refers to positive. So if you replace the silicon with something to the left of it, it has one less electron than silicon does in its valence orbitals. And now you've created a positive hole, an absence of electron in that space. And it can propagate under the right conditions. And the combination of N-type and P-type semiconductors is one way of getting various types of electronic devices to work. So on this side, we have an extra electron that's able to move into the conduction band. And on this side, we have an absence of electrons. We call, and for convenience, they're called holes. So the N-types have extra valence electrons, and the P-types have holes. So electrons can move into those holes, but when you move an electron into a hole, you create a hole behind it. So in effect, the electron moves one direction and the hole moves the other. Okay, so this is what it would look like. Arsenic is to the right of silicon, so it's got an extra valence electron making an N-type. And, boron is to the left of silicon. It has an absence of one electron and creates a hole. Okay, now let's focus in on ionic solids. Ionic solids are very stable. They have very high melting points, and they're held together by electrostatic forces between complete ions, positive, negative, is the force attracting them together. And they're usually arranged in regular crystal structure. So how do we account for the difference in melting point? Let's see. I have to beg off for just 3 minutes bathroom break. I'll be right back. Okay, I'm back. If you ever have a chance to develop high blood pressure, don't do it, because they'll put you on water pills, and they fill up your bladder pretty quick. Okay, so for these ionic solids, what then would be, we talk about the melting point of solids, right? You add so much heat to them. So what's happening when you add heat? You're breaking those intermolecular bonds, or you're weakening them so that they can move past one another, going from a solid to a liquid. So what's responsible for the difference in melting points? Well, obviously, the strength of the attraction. So the stronger the attraction between the cations and anions, the higher the melting point, right? So what's responsible for the strength of those attractions? Well, remember Coulomb's law. Maybe you remember, maybe you don't. Coulomb's law says that the force of attraction between two opposite charges is proportional to the size of the charge and inversely proportional to the square of the distance between the charges, right? So there's your proportionality constant, or Coulomb's constant. And then you have the distance between the two. The size of the charge. So you have the positive charge and the negative charge, whatever that happens to be, right? Those are not proper variables, but I'm just illustrating. And then the distance between them, r squared. So as the charges increase in size, the force increases, and consequently, the melting point goes up. Or the distance between them decreases, smaller denominator makes for a larger quotient, which is the force. So if they can get closer together, then the force increases and the melting point goes up, right? So how do we do that in reality? Well, here are two examples, sodium chloride and magnesium oxide. So in this case, you've got a +1 charge and a -1 charge providing the electrostatic attraction. And over here you have a 2+ charge and a 2- charge providing stronger attraction, right? The charges are increasing, right? So that's one thing. The other thing is the size of the ions. The size of the sodium and the chloride ions are bigger than the magnesium and the oxide ions. So that puts the centers of those charges closer together for the magnesium oxide, and the closer you get together, the stronger the force. So those two things together, size of the charge and the distance between the charges, determines the magnitude of the intermolecular force attracting them together, consequently, the melting point. So the melting point for sodium chloride should be lower than for magnesium oxide. Now we think back to the video and what type of holes are there, right? One mentioned, when we were talking about two dimensionals, we said, okay, here's a trigonal hole, right? Because we have 3 of these spheres touching one another. Oops, sorry, there we go. Usually for an ionic crystal made up of only 2, anion and cation, those holes are much too small. Well, actually, let me back up. If this layer is composed of the anion, then we can't fit the cation inside that hole. It's just too small. So where is the cation going to reside? It's in another layer. It's up here, above that hole, usually. So the trigonal holes are too small. So in this closest packed structure, what other types of holes are there? Well, there was a mention of a tetrahedral hole, right? So the tetrahedral hole is composed of these sulfur anions, and then in the middle is a hole that's sufficiently large enough for the zinc 2+ ion to fit in there. So we can talk about the closest packing structure in terms of the anion only. The sulfide, right? Sulfide like this. So that ion constitutes the tetrahedral structure with a hole inside of it occupied by the zinc. Another type of hole, octahedral hole. The octahedral hole is much bigger, right? So when we're looking for ionic solids that can be accommodated here, then we look for those where basically the size of the anions and the cations are pretty close together. So we've got room in that octahedral hole to fit our large cation. So in short, we're looking at the holes in these structures. The trigonal hole is the smallest. Tetrahedral is the next size, largest size hole, and the octahedral is the largest size hole. Okay, I'm not going to spend time on this chart. It's in your book. And it just summarizes everything we've included so far. Atomic solids, molecular solids, ionic solids. So we've discussed each one of these in turn. It may not be obvious to you with the flow of the lecture, but we have at one point or another discussed atomic solids versus molecular solids versus ionic solids. Now, for the last thing, we want to look at various changes of state and how they can be explained by intermolecular forces. So let's start off with vapor pressure. We have to define what vapor pressure is. Vapor pressure is defined in terms of a closed vessel with a liquid in part of the vessel and what we call headspace in the rest of the vessel. So it's got to be enclosed to develop this vapor pressure that we talk about. If it's open to the atmosphere, there'll never be any vapor pressure developed. Right? You start off with a pure liquid as you close the vessel. There may be other gases in here, but there is a pure liquid that is losing molecules or atoms from its surface. And when it starts out, it's unidirectional. It only goes one way. Starts out losing molecules from the surface, and they occupy this headspace. But eventually, it's a gas, right? They're moving around, they're bouncing around, they're bouncing off the walls, they're bouncing off the cork, they're bouncing off the surface of the liquid. Well, sometimes when they hit the surface of the liquid, they go back into the liquid form. Right? And the more gas atoms or molecules from the liquid you have in the headspace, the higher the rate of return. So you start off with all of these atoms or molecules leaving the surface and nothing returning. And eventually you get enough up in the headspace that some of them start to return. And you reach a point where the rate of both processes, leaving and returning, are equal. At that point, you have developed a vapor pressure for that liquid. It's characteristic of that liquid. And this is what it would look like over time. This is the rate of condensation, that is return from gas to liquid. And this is the rate of evaporation, which really never changes. It starts off at this rate, stays that rate. But if the rate of return is now the same rate, then macroscopically, it looks like nothing's happening. For liquids that have a very high vapor pressure, you may see a certain level, and over time, you'll see that level drop. But at some point, the level doesn't drop anymore because you're getting the two rates are balanced. They're in equilibrium. Okay, I got 15 minutes. I think I can cover the rest in 15 minutes. So, by definition, the pressure, vapor pressure, is the pressure of the vapor present at equilibrium above the surface of the liquid. Now, why does it develop that vapor pressure? Well, it's all dependent upon the intermolecular forces holding the molecules or atoms in the liquid state. If they're very weak forces, then you get large shift of liquid to vapor, and the vapor pressure will be high. But if the forces are very small, then you get low vapor pressure in the headspace above. So water has a vapor pressure, but the vapor pressure is also dependent upon temperature. Remember, if you add energy in the form of temperature to a liquid, then you add enough energy to break those bonds, and you get more vapor as a consequence. So as you increase the temperature, you also increase the vapor pressure. But there comes a time when the vapor pressure cannot get any higher. And that depends on the pressure opposing it, right? So if the pressure opposing it is a certain amount, then it will reach a point where you change liquid into vapor let's see, I painted myself into a corner. You reach a point where you're breaking the bonds and you're evaporating liquid. But now, if you open the container, the only thing that is opposing it is whatever the pressure outside is. Okay? And if you decrease that pressure above the headspace, you continue to decrease it, then it takes less energy to expel liquid into gas phase. Okay? So the temperature required to do that drops. The amount of energy drops. So that's why it's important to know what is the pressure, starting pressure above that liquid. If that pressure is 1 atmosphere, then the point at which the vapor is expelled is known as the boiling point. And the boiling point for water at 1 atmosphere is 100 degrees centigrade. But if you go to a higher altitude, then you have less opposing pressure in the atmosphere, and it takes less energy to vaporize the liquid. So the boiling point will decrease below 100, to the point that if you're on top of Mount Everest, the boiling point of water is like in the low 80s or maybe the high 70s. That's why when you're at the increased altitude, it takes longer to cook your food. Right? At 1 mile high in Denver, it takes longer. Instead of a 4-minute egg, you may have to go for a 6-minute egg to get the same consistency because the temperature's lower of the water. Even though it's boiling, temperature's still lower. Now, what's another way to measure vapor pressure? Well, you can use a barometer, right? If there's a vacuum above the column of mercury, then the column is going to be 760 torr, or millimeters high. If you put water in that space and then allow it to equilibrate, you're going to get a certain pressure there. And for water, that pressure is 24 torr. And that's at standard temperature, which would be 25 degrees centigrade for solids and liquids. But if you put something that's more volatile, that has lower attractive forces, intermolecular forces, then you should get a higher pressure. And that's what we see. For ethanol, we get 65 torr is the vapor pressure. For dimethyl ether, we get 545 torr. So the difference in that, actually we get 215 torr, excuse me. And the difference in that is the vapor pressure, 545 torr. So we can see qualitatively the difference in intermolecular forces between water and ethanol and diethyl ether are decreased from left to right on this slide. Okay, so like I said before, as the temperature increases, we get an increase in vapor pressure, and it's characteristic of the different substance based upon the intermolecular forces that are at play. So we see this curve for water. The vapor pressure increases until we get to 100 degrees, and then the vapor pressure is 760 torr. 78 torr for ethanol, 78 degrees for ethanol, excuse me, and 35 degrees for diethyl ether. Now, how do we express these intermolecular forces, right? They can be quantified. They can be given a delta H, or an enthalpy of vaporization. And that value can be calculated. This is the basic differential equation, right? The Clausius-Clapeyron equation. But there's an integrated form that works better, right? We talked about differential versus integrated equations in our discussion of, oh, no, we haven't talked about that. I'm sorry. We will talk about that when we talk about kinetics. This is known as the differential equation, and an integrative equation is described here. This one in the bottom, right there. So the relationship of the vapor pressure to the delta H of vaporization is here, and it's dependent upon temperature. So we develop a modified equation which incorporates two different temperatures, two different vapor pressures, and the delta H, the enthalpy of vaporization. So all we have to do is conduct two experiments. We measure the vapor pressure at this temperature and the vapor pressure at that temperature. Now we have an equation in one unknown. We solve for delta H. So be looking for those types of solutions, those problems, in your review document. Notice also that the R value, the universal gas constant, takes a different form for this equation. Why? Because this is not pressure and volume, as in previous equations where we use the liter atmospheres per mole K. This one is energy, so we use joules per mole K. And this is the value for that one. So be sure and use that correctly. And the temperature also has to be converted to Kelvin. Don't forget that. Okay. This is an example. I'm running out of time, so I'm not going to go through this example, but it allows you to calculate the vapor pressure of water at a different temperature using the same equation, but now it has a different unknown. The unknown now is the vapor pressure of water at this temperature, and we're given the heat of vaporization, or the enthalpy of vaporization here, 43.9. So we can calculate the vapor pressure at a different temperature. This is known as a step diagram for phase changes. So as we take ice and heat it up, right, different temperature, then we notice that as we add heat, as long as it's solid, then we're increasing the temperature, or the average kinetic energy of all the molecules, and they're vibrating as we add energy. But when we start making ice, when we melt it, then the temperature stops because now the energy is being used to break those bonds and make liquid. Now, once we have liquid and nothing else, then we're adding energy to the vibrational and translational motion of those water molecules, and the temperature increases until we start making steam at the boiling point. Now all the energy is going into breaking those bonds and making gas. And when all the liquid water is gone, now the only place that the energy can go is into increasing the temperature of the steam. So whenever you have two phases together, temperature is stable. Okay, which would you predict, and I mentioned this earlier, would be larger? The energy of vaporization or the energy of fusion? The delta H for fusion is just how much energy does it take to change solid into liquid. And the delta H for vaporization is from liquid to gas. So think about it. What are we doing when we're going from solid to liquid? We're just weakening those bonds so the molecules can slide past one another. That takes a little bit of energy. So the delta H would be relatively low. Whereas the delta H of vaporization, we're actually breaking all intermolecular forces. Most of them anyway. So that we make a gas. And that takes a lot more energy. So delta H of vaporization should be greater than delta H of fusion. And I just gave you an explanation for that. Now, what's a phase diagram? Okay, I'm going to go over. So I'll finish this and then come back immediately to the lab session. In order to get to the lab session, you need to go into Blackboard and find the Zoom, the left-hand panel, click on that, and find the day and the time, 12 noon, for that meeting, and you'll be reconnected to me as soon as I'm finished with this. Okay, so we have various characteristics of the phase diagram, and they can be very complex or they can be very simple, and we're going to concentrate on a simple phase diagram. So a phase diagram is opposing pressure on one axis and temperature on the other, and these lines represent phase boundaries. So at this temperature and pressure, you have both solid and gas together. And here's the same thing, different pressure, different temperature, solid and gas. Here we have liquid and gas together at these temperatures and pressures, and so forth and so on. Now there's one point on this chart where you have all three phases together. That's the triple point. So at this pressure and this temperature, you have solid, liquid, gas together at the same time. And beyond, as you go up this liquid-gas boundary, you reach a point where it stops. And any place beyond that, out here, you have what's called a supercritical fluid. It has characteristics of gas and liquid at the same time. In other words, you can't tell the difference between the two. And that's the critical point. So if you were to hold the temperature constant and change the pressure, say hold the temperature here and increase the pressure, you would go from gas to solid. Or from here, you would go from gas to liquid. Or from here, you would go from liquid to solid. Or if you hold the pressure constant and change the temperature, you would go here, you would go from solid to liquid across that boundary. Or from liquid to gas across that boundary. Or still holding the pressure constant, you might go from solid to gas. And that's what happens with dry ice. It goes from solid to gas because we've got 1 atmosphere pressure and you're increasing the temperature. This is probably CO2. Oh yeah, there it is, carbon dioxide. 78 degrees, 78.5 actually, is the temperature at which solid carbon dioxide, dry ice, sublimates. Okay? Now there's some compounds or substances that fly in the face of that norm. But notice that this line right here between solid and liquid has a positive slope. Well, the way you're looking at it, the other way. Positive slope. But for water, it has a negative slope. So if you hold the temperature constant and you increase the pressure, you go from solid to liquid rather than from liquid to solid. Now, what happens to these various physical properties of a substance when you increase the intermolecular forces? Increase the forces between molecules, takes more to vaporize them, you increase the boiling point. If the forces are stronger, you increase the viscosity as well. The forces are stronger, the surface temperature increases. The enthalpy of fusion increases. The freezing point increases, all as the intermolecular forces increase. But as you increase the intermolecular forces, the vapor pressure goes down because your stronger forces are holding that liquid in the liquid phase. So the vapor pressure decreases. And the heat of vaporization also increases. So the only one, upon increasing intermolecular forces, the vapor pressure decreases, the rest increase. Okay, I'm done. 4 minutes over. So I'll stop the share. And we'll stop the recording and I'll migrate to CHEM104 and talk about that in terms of what's expected and so forth and so on.